Okay, 1912, synthetic strategies. So we've built a lot of reactions this chapter, chapter 19. And it's time to go back and say, what can we do with these, right? So you know how to make, for example, bromobenzene from benzene, right? We started the chapter out by saying we're going to learn to make, these two. We're going to learn to make nitrobenzene, benzene sulfonic acid, and so on. That was how we started out this chapter. Now, when we learned to make, and now we've done it, right? So now that you know how to make nitrobenzene, we also added in a cool little reaction here, how to make aniline from that. Okay, you knew from last chapter how to take an alkyl benzene and add bromine to the benzylic position, right? That's the benzylic position. You know from chapter 18 how to take an alkyl benzene and convert that to benzoic acid, right? And you learned in this chapter when you did acylation, there's my acyl group, you learned how to change that to an alkyl group. This is kind of cool, right? Because this is a deactivator and it's a meta director, right? And this is an activator and an ortho para director. Okay, so we're going to find, as we're trying to build things, that can be a useful distinction. All right, so let's talk about some ways to synthesize things, or some strategies that we can consider. So to synthesize dye-substituted aromatic compounds, you have to carefully think about what direction is going on. For example, how would you make 3-nitrobromobenzene? Okay, so here's my bromine, or rather, I'm sorry, my benzene. I didn't leave enough room up here at the top for that. Let that be a carbon here, which is not very well drawn. 1, 2, 3 nitrobromobenzene. Right. So if we're going to make this, you can't just put a bromine on there and then a nitro, or rather, you can't have. There's not two good ways to make this. First a bromine, then a nitro, or then a nitro and then a bromine. If you do the nitro first, there's two problems that go on, right? Let me cut away to, I'm going to keep these, cut away to my whiteboard, which I think I left some notes on here. I did, yeah, let's get rid of these. Let's get rid of these notes. Oh gosh, I forget how to do this. I don't use this whiteboard enough. I think yeah, there we go. So let's do that, delete. Let's go back to this. I think that, yeah, okay. Control Z, escape. How do I deselect that? Oh, I don't use this enough. Give me 1 second. I want to deselect this. Edit, clear, select all, deselect, Control D. Okay, good, there we go. All right, so the question was, how do we make 1,3-bromobenzene, right? Or rather, 3-nitrobromobenzene. That was the question. So we could either, from benzene, right? So we could either, first from benzene, this is a little bit tedious but important, okay? So watch this. We could either take benzene and first add the bromo group, right? And then the nitro group. But there's a problem with this. What's the problem? This doesn't work, right? And furthermore, we could, coming from a different perspective, we could add the nitro group first. Wait. Yeah. That's right. I'm sort of drawing backwards. My arrow's backwards, and it's confusing me. So I could take my benzene and I could add the nitro first. I'm going to take a second, pretend like I'm trying to remember these reactions, and I'm going to write out the reactants here. This is an excellent, effective way to memorize H2SO4, the reactions, right? And this would be bromine in FeBr3, or iron 3 bromide, right? And this over here, going from benzene to that, would be bromine, and I'm pretending like I'm trying to remember these, right? So this time I'm going to go, oh yeah, I could also do aluminum. bromide, right? And then here, from here to here, that would be nitric acid and sulfuric acid. You can only do this so many times, and you're going to eventually memorize these just cold. It'll be so easy. All right, so there's a problem going from here. This works. There's no problem with that. And this now is a meta director, right? It's a meta director, and it's a deactivator. So that's a problem, actually, right? If it's a deactivator, this is not going to go on in good yield. This reaction is not necessarily very good because it's deactivating. But it is going in the right place. It's meta. Agreed? Okay. What about this way? Going from, this works, of course, brominating a benzene ring, that works. But what about nitrating in the meta position? Well, this is an OP director, right? And it's a deactivator. Okay? Folks, if that's not familiar to you, go to page 899 and look at table, I think it's 19.1, and review that. Again, so much you can review when you're doing synthesis, and you should. All right, so you can see that there's some problems here. That's what this section is about. Section 1912 is about working through these problems. So another question is, how might you make 3-chloroaniline? And I'm not going to go back to my whiteboard here and do that, but you might pause the video now and draw that out and say, what's the problems with this? While you're doing that, you will be reviewing the reactions. Please consider doing it. Okay, so this reaction that's described above is more challenging than the one described before because the amino group and the chloro group are both para-directing, right? And you would remember that if you go back, oops, whoa, wait a second, sorry. Gotta get back to my Shift F5. Okay, they're both para-directing, and you would remember that if you first of all draw 3-chloroaniline, you're practicing nomenclature, you're practicing lots of things when you do that, and then you're also practicing your reactions because you draw a reaction scheme like I did a moment ago. So anyway, go do that. I hope you did. All right, let's suppose you did. Now, a meta director has to be used if you're going to put something in the 3 position. And both of these are ortho-para-directing, right? So one of the groups will, so you'll have to have a meta director on there and then make a conversion so that you get, so that you convert the meta director to either amino or to the chloro position. All right, that's subtle. Let's look at some examples on the next slide. So, for example, here's an example. You have an OP director here, right? And you have a meta director here, right? So I could put nitro on first. In the previous example, I could put nitro on, put something in the meta position, and then convert to amino by reducing with zinc and hydrochloric acid, right? Or in another example, if I want to put, I could put something in the OP position by using a methyl group and then convert it to an acyl group, which in this case is a carboxylic acid, right? Remember this reaction from chapter 18? Okay. Another example is I could put something in the meta position by putting an acyl group on there and then using a Clemmensen reduction to make it an alkyl group, right? You see how you can have a group on there that's a meta director and then change it to an OP director, right? We've got lots of these reactions in place. Some of you have been practicing this because when you were memorizing these reactions, you were saying to yourself, why? Why are we asked to know this reaction? And that's the reason why. This is it. We've been leading up to this point. Okay, so let's move on. There are limitations that you need to be aware of. For example, nitration conditions generally cause amine oxidation, leading to a mixture of undesired products. So you really can't nitrate something that's got an amino group on it. It's not going to work. This is not going to work. See that? If I tried nitric acid and sulfuric acid, this will not work By the way, do you see how I'm reviewing this reaction every time I'm talking about this? I'm taking my time, and I'm looking up those details, and I'm writing them down, and I'm saying them out loud. If you're doing the same thing, you need to do it. So useful. All right. Now, another problem is that Friedel-Crafts reactions are too slow when a deactivating group is present on the ring. Oh, wow. What? Seriously? Oh, no. I can't just put a methyl group on there? No, you can't. All right. Or if you have a strong a moderate deactivator, still no reaction. Strong deactivator is even worse. Right. So go practice Skill Builder 19.5 and look back at these notes while you're doing that, if helpful. Okay. So now design a synthesis for the molecule below, starting from benzene. I think I'm going to, since this video is a little bit long, but the whole lesson is here in section 19.12. I'm going to give an example. I'm going to give a solution to this. So go design a synthesis, pause the video now, and come back. Okay, I'm going to suppose that you did it. Now, what I'm going to do is I'm going to make using a couple different colors here. Dicarboxylic acid from two different ways. Okay, one is better than the other. I'm going to take this, go a little bit thinner. Okay, I'm gonna go red. Let's go red from the one side. All right, so I'm gonna first of all say that I'm gonna do what I think probably is the most common solution from students on this, and not the best. Let's suppose we've got two methyl groups here, and we're gonna burn this off with potassium permanganate. Right? This is from chapter 18. KMNO4, step 1, step 2. Let's go back and review the reaction here that can do that. Okay? You see how it's potassium permanganate, sodium hydroxide, and heat, potassium permanganate, and then follow it with acid. Okay? So back over here, potassium permanganate, sodium hydroxide, and heat, and then we follow this up with acid, right? Okay, so this is a reaction that we got from chapter 18. I don't remember what page it's on. If it's not familiar, you should go back and look at it, okay? So here, okay, this is just one step, rather two steps, I guess, but it's two steps of the same thing, right? AlCl3. If this is not familiar to you, you should write this out. You should say something about this. This is a Friedel-Crafts alkylation. Okay? All right, so this works, but what's the problem with this? The problem is that you're going to get a bunch of, well, first of all, you're going to get polyalkylation, in which case you've got this thing over here too. All right, let me get rid of those. You got polyalkylation. You have para substitution instead of ortho, right? So this is not the best way. The best way is to get it from that. With, I'm going to write it out again, say it, potassium permanganate, sodium hydroxide, and heat, and then follow this up with acid. If you do this a bunch of times, you will accidentally memorize these reactions, okay? Now this, 1, 2, 3, 4. So 1, 2, 3, 4. And then right? 1, 2, 3, 4. 1, 2, 3, 4. Aha! Look at that. AlCl3, aluminum chloride, and this comes from plus 1, 2, 3, 4. A chloro here and a chloro here. 1, 2, 3, 4. Wow. Oh, that's beautiful. And that's done in aluminum chloride. That is beautiful. So you can see that I have forced this to go in the OP, because if you take a four carbon structure like this and try to put that para, it's not going to work. I'm going to say that again. I know that's a little subtle. I'm forcing ortho by using a chain, really, right? It's a tether by using a small chain to make para too far. Para is too far away. Okay, so both of those are good, are decent methods. There's one that's really good, and the other one is okay. So this is what synthesis is all about. It can be very frustrating to students, especially if you're thinking, well, I don't know. There's sort of a way of thinking when you're first in college, where you think that there's some right answer, and what was the answer supposed to be, and so on, right? But synthesis is beyond that. Synthesis is what's good and what's better, and that can be frustrating for students. I acknowledge that right here and now. I will also say, though, I do believe in it. I think it's a fantastic way to give the students a chance to think deeply, which is better, which is inaccessible when you're simply learning, cold hard facts, right? Okay, so let's move on now. When designing a synthesis for polysubstituted aromatic compounds, often retrosynthetic analysis is helpful. So what we mean by that is we say, well, I did a retrosynthetic analysis here. I said, I'll start with the end and think what might have come upstream of that, right? That's retrosynthesis. And let me go further and say, let me add here. Let me go further and say that retrosynthesis, a lot of textbooks, including Klein, will oftentimes say, we'll use a weird symbol, okay? And here's the weird symbol. They're going to say, how do you make this is just the same thing I had in the previous slide, right? How do you make this from benzene? Okay? This is to be read. Make this from. That's how this symbol is to be read. All right, and this is called retrosynthesis because we're oftentimes thinking, well, I mean, obviously there's a billion things I can do with this, right? A billion things. So sometimes you're going to say, well, I know there's so many things I can do from that. There's just too many possibilities. Let's think what could give us that, right? So we're working our way backwards, and that's why it's called retrosynthesis. All right, so look at this now. When designing a synthesis okay, so design a synthesis for this thing right here. Let me go back to my whiteboard now. I think I can do this. Okay, so it looks like it's an acyl group. It's a three carbon acyl group here, and a bromo across from it, a nitro next to it. Okay, I think I can remember that. So let's go here and say we want to make 1, 2, 3. Bromo across from it. Okay, don't forget it's benzene. It's simply not going to work if it's not that, right? And I think the nitro was right next to the benzene. Let's go back and look at this. Is that what that was? Yeah, these were across from each other, and the nitro was there, and it's a 1, 2, 3. That's exactly what that was. Okay, got mine in a slightly different orientation, but all right. So now that the question is, how might we make something like that? Well, let's consider what was the last guy to come on here. And this is what this slide is all about. I'm just going to do a lot of the work over here. So we might have said that the bromo was the last substituent. Right? Or we might have said that the last thing to come on here is the nitro group. Right? Or we might have said that the last group to come on here is, what did I say? Nitro, bromo, is the acyl group, right? Propanoyl, which we haven't learned a name yet, but okay. That's another possibility. Agreed? So these are the three possibilities that might have come from backwards. You need to pause the video right now and say, what's the problem with each of these? Well, there's one of them that's good. Only one that works. Okay, I'm going to suppose you paused the video. I really hope you're doing that. All right. So the problem with this is that this is a meta director, and this is a meta director, and there's two deactivators, by the way. And we already learned that Friedel-Crafts, or we learned Friedel-Crafts alkylation doesn't work with that. All right, so look at that. If these are both meta directors, the new substituent is going to have to go here, and it doesn't. So this does not work. No, no. Okay, what about this one? Well, this is a meta director, and this is an OP director. Does that work? That means that the new position is going to have to be here or here. And yeah, actually that works, because that's where it goes, right? You see that? So let's circle that for now. And what about this? This is a meta director, and this is a meta director, and this is an OP director. So the new group is either going to have to go here or here, right? Okay, so this is okay, except this is strongly deactivating. I should have put the note out here, right? That's a meta director, and this is an OP director, right? Do that, and you'll learn these things accidentally. It's beautiful. Great way to study. So now that I've got that, this is a meta director. Okay, so both of these actually work, okay? But one's better than the other one, because if I do this one, I'm going to have some contamination over here, right? So this is better for that reason, okay? But there's one more reason why this one's better, and that is that this is a strong deactivator, which I'm going to say D. Okay? This is a deactivator, and this is a deactivator, right? But this is a strong deactivator, right? So you see how this is if this is a stronger deactivator, and we know Friedel-Crafts alkylation doesn't work with nitro on it, that's a problem, because this is going to take a Friedel-Crafts acylation to get that on there, right? Okay, so that's another strike against it. So this is the one. That is retrosynthesis. Wow. All right, so what you should do now, pause the video again and think to yourself, what comes upstream of that? Lovely. Lovely. That's really a good example. Thank you, Klein, for giving us that example. All right, so I think this next slide tells us that the nitro group has to go last. Oops, there's your answer. Hopefully you paused it before you looked at this. Right? Beautiful. Okay, that's all I had to say about synthetic strategies. And of course, there's much, much more, but that's, I think, a good introduction to synthetic strategies. Good luck.